Okay, so today we begin chapter 4. This material will be on the second exam, and chapter 4 is about chemical quantities and aqueous reactions. It's where we first really get into chemical reactions and actually doing stuff with them. Under the topic in the first section that we're going to be concerned about is reaction stoichiometry. Reaction stoichiometry is section 4.2, and it has to do with the relationships of specific amounts of things to each other in a chemical reaction. And it's about the numerical relationship in terms of either molecules or moles of molecules of things to each other. And you can use stoichiometry to, relate products to reactants, but also reactants to products, or reactants to other reactants, or products to other products. Basically, any two things involved in a chemical reaction can be quantitatively related to each other through reaction stoichiometry. Stoichiometry depends on the coefficients that we use when we balance a chemical reaction, because those coefficients are what tell us the relative numbers of molecules or groups of molecules, like moles of molecules, of things that are involved in the reaction. So the coefficients in the chemical equation specify the relative amounts in moles or molecules of each substance involved. And from the balanced equation, you can relate moles of one substance to moles of any other substance in the reaction. Okay, so you basically relate moles of one thing to moles of anything else. An example is the combustion of butane, in which for every 2 moles of butane you burn, which is CH18, you use 25 moles of oxygen from the air, and you produce 16 moles of carbon dioxide and 18 moles of water. And this gives the relative ratios of these compounds to each other in that reaction. So however many moles of butane, or sorry, of octane you burn, you produce 16 over 2 times as many moles of CO2. Or in other words, 8 times as many moles of CO2. For every 2 moles of octane you burn, you need 25 moles of O2. So that means that the amount of oxygen you need is 25 over 2 compared to the moles of octane. Or in other words, you need 12.5 times as many moles of oxygen as you do octane, and so on and so on and so on. And so stoichiometry is more formally defined as the numerical relationships between the amounts in moles or molecules of the substances involved in a chemical reaction. So it's in a balanced chemical equation. Before you can actually take advantage of stoichiometry and use it to do anything, the equation does have to be balanced. Okay, the book uses an example of making a pizza. And actually, cooking examples or baking examples are fairly common in this area because a lot of chemical reactions occur very similarly to recipes, where you put in a certain amount of this and a certain amount of that, and you do this to it, and you get out a certain amount of the product. And in fact, the instructions for general chemistry labs of the type that we're using, where they basically say, do this, then do that, then do this other thing, and then measure this. And they're often called cookbook procedures because they lay out the steps in the chemical reaction just like in a cookbook. So there's a lot of connection between chemistry and cooking or baking. But anyway, for making a pizza, so for making the pizza, you have the recipe. And this isn't really detailed enough to be a recipe. It's more like a list of ingredients, where 1 crust and 5 ounces of tomato sauce and 2 cups of cheese will produce 1 pizza. And don't forget the baking. We'll put a little triangle over the arrow to remind you that you have to put it in the oven. Okay, so you can focus on ingredients versus products, where we have 1 crust for every 1 pizza. And we have 5 ounces of sauce for every 1 pizza. And we have 2 cups of cheese for every 1 pizza. And this, this is the ratio: 1 crust for every 1 pizza, 5 ounces sauce for every 1 pizza, and so on. And that's a comparison between each reactant individually and the amount of product that can be made. That's made from that amount of the ingredient. And you can also relate the ingredients to each other. So, for instance, you need 1 crust for every 5 ounces of sauce. You need 5 ounces of sauce for every 2 cups of cheese, and so on. So basically, if we have 2 cups of cheese, we know that we need 5 ounces of sauce. If we have 4 cups of cheese, then we need 10 ounces of sauce, and so on. And using techniques we're going to see in a moment, you can even use these ratios to compare amounts of ingredients that are not whole numbers. What if you had 3.57 cups of cheese? How many ounces of sauce would you need? That kind of thing. So you can use the recipe for ratios of things required. So things required. Let's say if I have 3.5 cups of cheese, how many ounces of sauce do I need? Okay, so mathematically, you can just take what you've got, 3.5 cups of cheese, and take the ratio of those 2 things from the balanced equation. In this case, it's 5 ounces of sauce for every 2 cups of cheese. So make sure that what you're starting with is on the bottom of this ratio, and what you want to end up with is on top of the ratio. Notice that cups of cheese as a unit cancel out, and you'd end up with 8.75 ounces of sauce. Okay, so this is actually not too complicated a subject. So if you have 7.62 ounces of sauce, how many pizzas would be possible? That's assuming that you have enough of the other ingredients. Because in most chemical reactions, what usually happens is that one of the reactants will eventually run out. And at that point, the reaction is over and you don't get any more product. In the case of a pizza, if you don't have enough of one of the reactants, the reaction doesn't really stop. You just get a funny tasting pizza. So, the analogy between chemistry and baking is not total. So that's assuming enough of the other ingredients. That would be 7.62 ounces of sauce times, and the ratio of pizza to sauce is 1 pizza for every 5 ounces of sauce. And that would give you 1.52 pizzas. So we're assuming here that we have a standard size for pizzas. Otherwise, we'd probably just say you get 1 big pizza and 1 little one. You can go the other way around. Whoops. If I want to make a certain number of pizzas, how much of the ingredients do I need? So if you want to make 3 pizzas, how much of each ingredient is required? Well, this isn't really all that difficult because, 3 is a whole number. So if you want 3 times as many pizzas as the recipe makes, then that means you need 3 times as many of each of the ingredients. But it does serve a purpose to set up easy examples like this so that you can use them as examples for harder problems later on. So we start out knowing we want 3 pizzas, and we need 1 crust for every 1 pizza. So surprise, surprise, we need 3 crusts for 3 pizzas. Again, also, if we want 3 pizzas, we need 5 ounces of sauce for each pizza. And surprise, surprise, we need 15 ounces of sauce. And again, we want 3 pizzas. We need 2 cups of cheese for every 1 pizza. And that means that we need 6 cups of cheese. So pretty straightforward as a concept. Sorry. And basically what we were doing is very similar to mole-to-mole conversions in chemical equations. Because like I said, chemical equations are set up in terms of either numbers of molecules, or you can think of that also as number of moles of molecules. And so if you want to convert from moles of something to moles of something else, all you really need is the ratio of numbers from the chemical equation. And our balanced equation for combustion of octane already showed us that the ratio of octane to carbon dioxide is 2 to 16. Or in other words, you get 16 over 2 times as much CO2 out as you had octane. Or in other words, 8 times as much carbon dioxide comes out in terms of number of moles as octane going in. And so, for example, if you burn 12.7 moles of octane in air, since the other ingredient is oxygen, saying that you're burning it in air is just another way of saying that you have more than enough oxygen. So that's why it's specified in air. So oxygen is not the reactant that's going to run out first. Octane will. How much carbon, or how many moles of carbon dioxide are produced? Okay, so if we know that we're burning 12.7 moles of octane, and the equation tells us that we get 16 moles of CO2 for every 2 moles of octane. Notice that moles of octane as a unit cancel out. We end up with 12.7 times 16 divided by 2, which is 102 moles of CO2. It's actually 101.6 something, but I've rounded it off to 3 significant figures because of 12.7. Okay, now that's very nice to be able to do, but it's not very often, or actually we can find out, I suppose, how many moles of reactants we're putting into a reaction and how many moles of products we're getting out. But it's not terribly convenient to measure out stuff that way. We usually measure out reactants in grams. And so what we really want to be able to do is mass-to-mass conversions. And the important thing to remember, though, about mass-to-mass conversions is that equations are not laid out in terms of mass. Equations are written and balanced in terms of numbers of molecules or groups of molecules like moles. Okay, so I'm just going to say moles, but you can also, of course, read the equations in terms of molecules. Okay, so moles, not mass. And what that means is that mass-to-mass conversions always have to go by way of moles. So if you're given a mass and you want to know how much mass of something else is produced, for instance, by a chemical reaction, you always have to take the moles or the mass of the thing you're given, change it to moles. Then and only then can you use the stoichiometry in the equation to change that to moles of the other thing. And then you have to change back the mass of the other thing. Okay, so for instance, if you're asked, you put in so many grams of compound A into the reaction, how much of product B results? Well, you first have to take mass of A and change to moles of A. Then you can change to moles of B. Then you can change to mass of B. And this middle step here, this is where the stoichiometry of the balanced equation comes in. The stoichiometry of the balanced equation plays no role in changing mass of A to moles of A, and no role in changing moles of B to mass of B. It's going from moles to moles where you use the stoichiometry. Okay, let's see. If, say, if 3.5 times 10 to the 15th grams of octane were burned in the world last year, how many grams of CO2 were produced from that? Okay, so we've got our equation. And this is already balanced. So we know the ratio of moles of one thing to another. And we're given a specific mass of octane. So what we're going to have to do is, first of all, change that to moles of octane. See, that's going mass of A to moles of A. Then, in step 2, we can change that to moles of CO2. Then in step 3, we can change that to grams of CO2. Unfortunately, there's no way to go directly from grams of one thing to grams of another. You always have to change it to moles first. Okay, I'm going to go to a new page, but I'll keep this up here so we can see what we're doing. So step 1 is where we go from grams of octane to moles of octane. So let's see, it was 3.5 times 10 to the 15th grams of C8H18. And there's 1 mole of C8H18 for every 414 grams of C8H18. And if we take 3.5 times 10 to the 15th power and divide by 114, we get 3.070 times 10 to the 13th moles of octane. The second step, again, is where the stoichiometry comes in. Now that we're here and we have moles of octane, we can take advantage of the 16:2 ratio in the equation to find out how many moles of CO2 we get. Okay, so we got 3.070 times 10 to the 13th moles of octane. And we get 16 moles of CO2 for every 2 moles of CH18. And that makes 2.456 times 10 to the 14th moles of CO2. Okay, so now we're here. Step 3 is where we go from moles of CO2 to grams of CO2. And we know how many moles of CO2 we have. And if you go to the periodic table and add up the masses, you'll find that there are 44 grams for every 1 mole of CO2. And that gives us 1.08 times 10 to the 16th grams of CO2. I guess by significant figures, this 3.5 times 10 to the 15th was only 2, so let's call it 1.1 times 10 to the 16 grams of CO2. And so we did it in the 3 steps. We went from moles to grams, or sorry, grams to moles, moles to moles, moles to grams. You don't have to do those 3 steps explicitly and separately like I did. I did it like that just to sort of illustrate the process. There's no reason that you couldn't just string the steps together and use one conversion factor after another. And another example will show you that. Magnesium hydroxide is the principal ingredient in milk of magnesia. And one of its main purposes is to neutralize excess stomach acid. Stomach acid is hydrochloric acid, or HCl. Technically, it has to be aqueous in order to be hydrochloric acid. And in the equation, magnesium hydroxide combines with 2 hydrochloric acids and produces 2 H2Os and 1 magnesium chloride. This can be read again in terms of molecules, and it can also be read in terms of moles. So for every, and actually it's important to keep in mind not just that the equation can be read in terms of moles, but that it's really the ratio of moles of one thing to another that we're concerned with. So it's not just that 1 mole of magnesium hydroxide combines with 2 moles of hydrochloric acid to produce 2 moles of H2O and 2 moles of magnesium chloride. The really important thing is that for every mole, for each mole of magnesium hydroxide, it reacts with 2 moles of hydrochloric acid and produces 2 moles of H2O for each mole of magnesium hydroxide and 1 mole of magnesium chloride for each mole of magnesium hydroxide. It's the ratios of one thing to another that are really useful in balanced chemical reactions. So you might wonder what mass of hydrochloric acid can be neutralized by 3.26 grams magnesium hydroxide. Well, this one, it's basically the same question we just had, only with different reactants. And in this case, though, we're comparing the amount of one reactant to the amount of another reactant. We have so much of this reactant, how much of that reactant would react with it. But similar to the previous example, if we want to go from grams to grams, we have to go by way of moles. And I'm going to do this all on one line just to show you that, how to do that. So if we have 3.26 grams of MgOH2, and there's 1 mole of MgOH2 for every 58.3 grams. And again, you get that by adding up the masses of magnesium and 2 oxygens and 2 hydrogens from the periodic table. And so now notice that grams of magnesium hydroxide will cancel out, and we would have moles of magnesium hydroxide at this point. But you don't have to stop and write down the moles of magnesium hydroxide. You can keep on going and change that to moles of hydrochloric acid just by using the stoichiometric ratio from the equation. There's 2 moles of HCl for every 1 mole of magnesium hydroxide. So now moles of magnesium hydroxide cancel out, and we would have moles of hydrochloric acid, but we want mass of hydrochloric acid. So you go to the periodic table and find out the mass of each mole of hydrochloric acid by adding up the mass of 1 hydrogen and 1 chlorine. And you get 36.5 grams of hydrochloric acid for every 1 mole of hydrochloric acid. And now moles of HCl cancel out. And you end up with grams of HCl as the only unit left. And so now you can just go right across and take 3.26 divided by 58.3 times 2 times 36.5. And that should come out to be 4.08 grams of HCl. Okay, so that's another example there. Now, as I've been saying, whenever you want to go, or sorry, whenever you do a chemical reaction and you add specific amounts of one reactant and another reactant, it's possible that you might be adding exactly the right amounts of those reactants to react with each other exactly with nothing left over. However, it's much more likely that you're adding more of one of the reactants relative to what's required than the other reactant. And in that case, what happens is one of the reactants will run out before the other one does. And at that point, the reaction is done. The reactant that runs out first is known as the limiting reactant or limiting reagent. And it's called that because once it runs out, the reaction is done and you get no more product. So that reactant that runs out first is the one that limits how much product you can get. And that's what we're going to do in the next section, in the next segment of the video, but that's for part B. So see you in a minute.